Alright, welcome everyone. This video, we're going to start talking about the thermodynamics of mixing. So in a previous video, we talked about partial molar quantities, which are some of the descriptors we'll use to describe mixtures. Okay, and now we'll start talking about things about like free energy of mixing and entropy of mixing. So let's consider first mixing of ideal gases, right? It's always a good place to start. Gases know molecular forces and things like that, right? Very simple type of system, right? So it's considered two containers, or a container, right, that's split into two sides. One side has moles of A, one side has moles of B, right? They're different number of moles of A and B, okay? But they both have the same temperature and pressure, right? So the pressure of A and the pressure of B, right, are the same inside their containers, right? So in this picture, right, there's a larger volume for B, and that's because there are more moles of B, right? So let's consider now, right, where we open the container, right, keeping the total pressure and temperature constant within the system, right? Right, and then in which case, right, now the total pressure is still P, total temperature is still T, but now the pressures of A and B have decreased, right? There are partial pressures now, we can consider them, right? And the pressures have decreased because the volumes increased for those gases, right? So I've opened up the wall between these two containers, right? The volumes have increased for both A and B, so their pressures have dropped, but because initially their pressures were equal to each other, right, the total pressure still end up going to be the same pressure P, okay? So, right, so this is kind of the system we're considering, right? So let's think about how the free energy changes for this system, okay? So, right, again, recall that any change in free energy is going to be related to a volume times change of pressure minus entropy times change in temperature plus change in number of moles times chemical potential, right, and the sum of that, okay? Now, at constant temperature and composition, right, composition meaning, right, that moles aren't changing, right, not any chemical reactions, no phase changes, right, then this change in gives free energy is just related with volume times change of pressure, okay, right, so G1 minus G2 or delta G, right, is just the integral of volume times change in pressure, okay. Now for an ideal gas, that volume is equal to nRT divided by pressure, right, so you get the integral is nRT ln P2 over P1, okay. And so if we divide everything by the number of moles, right, then for change in Gibbs free energy of some substance, right, is related with the change in chemical potential of some substance. So the final chemical potential, right, is like mu final equals mu initial plus RT ln P final divided by P initial, right? And this equation here is very important. Now we'll kind of talk about some, using this equation and other things, right? But this kind of equation, right, is showing you how the chemical potential of a gas changes with a change in pressure, okay? Which is very important. We'll use that often when we talk about mixtures of compounds, when we talk about colligative properties and other things like that. We'll come back to and equilibrium constants. All of this will come back to how the chemical potential changes with pressure. Okay. Now, again, we're considering an ideal gas, right? Let's consider now that my initial pressure is, say, our standard pressure, 1 bar, okay? And so we're going to call that initial chemical potential our standard chemical potential, mu naught, okay? So then, right, the pressure, the chemical potential of a gas, given some pressure of that gas, is just equal to its standard chemical potential plus RT ln of P of the gas, right, the partial pressure of the gas, okay? And so this is going to be true for any gas, right, or any ideal gas, right? Satisfy this relationship, okay? And so let's consider now for some mixture, okay, where the total Gibbs free energy, right, is related to the chemical potentials of, the partial molar chemical potentials of A partial molar chemical potential to B times the number of moles, right? So before that mixture, right, I have, these total Gibbs energy in my system, right, before things are mixed, right, it's just chemical potential of A times the number of moles of A, chemical potential of B times the number of moles of B, right, and the chemical potential of A and B are just related with their standard chemical potentials plus RT ln of P, right? They both have the same pressure initially, right? This is the problem we were considering, right? They both have the same partial pressure initially that we called P, okay? And they're both at the same temperature. So this is my initial, right, Gibbs free energy. Now, right, the total pressure after mixing these two things is still P, right? But the partial pressures of the gases are now different, okay? And so after I've mixed these things, right, I now have that the total Gibbs energy after mixing, think of this as like G final, right, is related with the chemical potential of A mixed times the number of moles of A plus chemical potential of B mixed times the number of moles of B. Okay, and then that change in Gibbs free energy, right, which would be the Gibbs free energy change of mixing, right, is related to the mixed Gibbs free energy minus the pure, right? The mixed, right, the chemical potential of A mixed, right, is just going to be its standard chemical potential plus RT ln of the partial pressure of A after things have been mixed, right? And the same thing here with B, right? And again, there's nothing else that's popping up here because we're talking about ideal gases, right? Which are have no intermolecular forces and things of that nature, okay? And then we again have the pure compound that we started off with given here, right? So if you simplify this, okay, you will get this Gibbs free energy of mixing of two gases. That you get the number of moles of A times RT ln PA over P plus R number of moles of B times RT ln PB over P. Okay, and this is true for mixing any ideal gases, right? Okay. And so again, we have this mixing now, right, for a gas, right, the partial pressure of A times the total pressure P, or divided by the total pressure P, right, is just the mole fraction of A, okay? And so I can rewrite this equation as just, okay, pulling out nRT from everything, okay, you can rewrite this equation as nRT times mole fraction of A times the logarithm of the mole fraction of A plus mole fraction of B times the natural logarithm of the mole fraction of B, okay? Okay, now this equation here, right, for mixing assumes constant temperature mixing, okay? Right, it also is assuming, right, the initial pressures of the gases are equal, right? And then the sum of the final pressures of the mixtures are equal to what the initial pressure of the gases were. Okay, so we used a number of assumptions along this path to get this Gibbs free energy change of mixing of two gases. Okay, right. Now note here that the mole fraction is always a number less than 1, so those natural logs are always going to be negative values. So this delta G of mixing for an ideal gas is always going to be negative, right? And to no one's surprise, right, at constant temperature pressure conditions, right, the mixing of two gases is always spontaneous, right? So we could think of, right, what is kind of the maximum free energy change that we can get, right, when mixing two gases. What's kind of the maximum value of that mole fraction of A? Right, you look at kind of the plot here, right, you'll see that it's at 0.5, right, which makes sense, right? The maximum free energy change is when you are mixing an equal amount of two species, right? Because that's when you get the most mixing occurring. Now, let's talk about some of the other functions, right? So we can look at, say, entropy, right? Which is related with the derivative of the Gibbs free energy with respect to temperature, assuming constant pressure, okay? So take our definition of the free energy change of mixing, okay? Take that derivative with respect to temperature, right? And you get the entropy change of mixing is just minus NR times those mole fraction functions and such, right? And you notice again that this is always going to be a positive entropy change, okay? And that's because, right, these are ideal gases, and we should expect these ideal gases to have an increase in entropy whenever mixing them, right? And the note here, right, that the relationship here, delta S with delta G, kind of shows, right, if you think about, again, delta G equaling delta H minus T delta S, right, the delta H here is equal to 0, right, which is not surprising, because I'm talking about an isothermal expansion of an ideal gas, right, which has an enthalpy change equal to 0, right, because there are no intermolecular forces between these gas particles and things of that nature, right? So there's no enthalpy change for an ideal gas specifically, okay?